Okay, hi y'all. Today we are going to walk through 8.3, which is graphing polar equations. So last class, if you remember, what we did was just focus on graphing points. So we learned that on a polar coordinate system, we are graphing r and theta. We also learned how to go back and forth between rectangular coordinates x, y to polar r and theta. We found that we can always compute the x coordinate using r times the cosine of theta. Y is always r times the sine of theta. So this is just how we were going from polar to rectangular to plot a point in the same exact location, but in different ways from polar to Cartesian. Now what we're going to do is expand this a little bit and start looking at not just graphing single points on the polar coordinate system, but actual equations. So what you were used to in rectangular world is graphing equations in the form of y equals and then some function of x. Like if we're talking about quadratics, x squared, whatever. So we're used to graphing y equals something in terms of x. In polar, when we're graphing polar graphs, typically what we're going to see is equations given by r equals. And then based on what comes after that, it's usually in terms of theta, it will generate different graphs. So that's just kind of a quick intro. I'm going to get right into it. Okay. All right, so we're going to start with the most simple polar graphs you're going to see, where you just have r equals a number or theta equals some specific value. So let's see what type of graphs are produced by these simple polar equations. So if the polar equation is just r equals 3, keeping in mind that we are talking about pairs of r and theta that make this equation true. Just like x's and y's, the xy pairs that make this equation true are on the graph of that equation. Same with this. The r theta pairs that are on this graph are going to form the full image. So this is a little confusing because all we have is r equals 3, which means it doesn't matter what theta is. Theta could be 0. Theta could be 45. Theta could be degrees. Theta could be 180 degrees. Oops, this should be 3, comma, 180. So let's see what graph is formed when I plot some of these points over here on my polar grid. So 3, comma, 0, that means I'm facing the 0 degrees and go out 3 units from the pole. There's my point. 3, comma, 45 degrees, that would be right here. Facing this direction, I'm going out 3. Facing 180, I'm going out 3. So we could do this forever. Basically, what's going to form is no matter what direction the rotation is, r equals 3. So I'm hoping right now it's starting to click what type of graph is formed by the equation r equals a number, and it's simply a circle. So we have not been able to graph circles with a single equation in x's and y's because circles aren't functions, but in polar graphs, we can. So we've got r equals 3. This generates a circle. This circle has a radius of 3. Hence the equation r equals 3. And it's centered at the pole. Usually we're used to calling that the origin. So one of the most basic polar graphs you guys are going to see, r equals a number. That's going to generate a circle with that radius r, whatever it is. Let's look at another simple equation, theta equals 45 degrees. This one, again, feels a little confusing because it is almost too simple. Remembering that we've got r, comma, theta. In this case, it's kind of the reverse. It doesn't matter what r is. Theta is always 45 degrees. So we could say r is 2. Theta is still 45 degrees. So that I would out towards 45, go 2, put a point. R could be -2, 45. So that means facing the 45, but going backwards, 1, 2. R could be 4. Theta is still 45. So I'm hoping right now it's starting to click what type of graph theta equals 45 degrees is going to produce, no matter what R is, we are always facing the 45-degree direction. This is going to form a line. We're used to graphing lines in rectangular form. That would just be y equals mx plus b. We also see lines being graphed in polar form simply by giving theta equals some rotation value. Okay, one last simple graph before we get into more complicated ones. Theta equals negative pi 6. Again, if it's just theta equals a value, right away we know this is going to be a line. It doesn't matter what r is. Theta is always going to be negative pi over 6. So when you rotate, if this is positive pi over 6, negative pi over 6, and then any r value on that line is going to generate the graph we're talking about. So we've got this line for theta equals negative pi over 6. So far you haven't seen anything that is unrecognizable. Circles and lines are things we're used to already. Let's see what type of graphs are produced by a little more involved polar equations. Okay, so if we come down here to example 2, we've got r equals. Again, most of our polar graphs are going to be in the form of r equals something depending on theta. To figure out our output and then start plotting our points, we just need to evaluate theta for a bunch of different values, a bunch of different rotations. For this, I want you to grab your calculator, turn it on. Because we have theta given to us in multiples of pi, basically, or expressions with pi, we want to, before we start crunching the numbers, make sure you go to your mode options, arrow down, and right now I'm in degree mode, so you can see degree highlighted black right here. Switch to radians, and now we're ready to plug in some values. So for sine theta, let's just, like, if you have any guesses of what this might look like, keep that in your mind right now. I don't expect you to have any idea of what this looks like, but I think it's interesting to hear what you guys think sometimes before you graph your first polar equations. I do want you to pay attention to patterns that you guys see from the next 3 examples, because there are a lot of patterns with polar graphs. So to figure out the r value when theta is 0, we're just plugging in 4 times the sine of 0. So 4 sine 0. Sine of 0 is 0, so no surprise that our output here is 0. So we've got the r of 0, theta 0, and we've got a point at the pole. This is the first point on our graph. And then we continue on. So 4 sine of pi over 6. Pi is right here above. Pi is right here above this caret button. So it's 4 sine pi over 6. We get 2. So we have the coordinate r is 2, theta is pi over 6. So opening up to pi over 6, and we count out 2 and plot a point there. Keep on going. So a quick trick here, let me zoom out a little so you can see my whole calculator. If you don't want to continue typing in this whole equation into your calculator, the option above the enter key down here, right here, is entry. You can hit second entry, and then it generates the exact same thing you just typed in. Then you can go back and just hit pi over 4 instead. So that'll save you some time. All right, let's round to about 2.8 here. And what I'm going to do right now is, instead of plotting 1 point at a time, I'm actually just going to evaluate these one at a time. I want you guys to go through these steps too. So you can do this quickly by just hitting second entry. Now I'm changing pi over 4 to pi over 3, enter, and I'll just round to the nearest tenth every time. So we've got 3.5. So I'm not going to plot all those points right now. Again, I'm just crunching the numbers first, trying to speed this up. So second entry, change pi over 3 to pi over 2. We get 4. Second entry, my next rotation for theta is 2 pi thirds. So 2 pi thirds, I get 3.5. Continuing on, we've got 3 pi over 4, 2.8. So you're noticing hopefully some symmetry here. So we had 2.8, 3.5, 4, 3.5, 2.8. Take a guess at what the next one's going to be. It's probably going to be 2. So we've got a second entry, 5 pi over 6. There we go. Pi is going to, sine of pi is 0. So that's definitely going to be 0. And then to know, each graph is different. So certain graphs, you're going to have to go all the way from 0 to 2 pi. Some of them you only need to go from 0 to pi. To know if you're done like getting these output values of R, when the values start to repeat, that's how you know. So if the very next one repeats back to 2 or 0, then we know that, oh, sorry, we just got 0. If the very next one starts to repeat these, then we know we're done. So one last time, 7 pi over 6. Oops. Oh, -2. Okay, I'm going to leave that there and show you what happens when we get that to that point, because it's confusing to know if we're done or not. Okay, let's start plotting these points. We already got R is 0, theta is 0. R is 2, theta is pi over 6. So now we're ready to do pi fourths, 2.8. You're just going to need to eyeball this for this point. So 1, 2.8 is close to 3, obviously not too far. Then we've got pi thirds, 3.5. Again, you're eyeballing 1, 2, 3.5. So plotting all of these points. Pi halves, we're going up to 4. 2 pi thirds, we've got 3.5. 1, 2, 3.5. So if you pause right here and look at what is taking shape, it looks like maybe a circle. Let's just keep going. So 3 pi fourths, 2.8. 1, 2.8-ish. Right here. 5 pi 6, and we go out 2. 1, 2. Pi, we go out 0. We're right back here. And then 7 pi over 6, we've got a y value or an r value of -2. So if I was facing this 7 pi over 6, I would have to go backwards 2, and that's where we land on the same point here. So even though it's -2, this is still taking us to repeat the value. So all of these would have negative r values right here, but we would still land on the points that we have just plotted. So if we connect all of our points here, we can see that we have just formed, if I can plot them somewhat accurately or connect them, we have formed a circle, which is really interesting coming from the circle we just graphed up here, which was given to us in the equation r equals 3. We found that a second equation, r equals 4 sine theta, has resulted in another circle. What I want you to pay attention to is radius, diameter, and center. Because when we have a circle, r equals 3, or r equals any number, center is at the origin or the pole. Radius is whatever that number is, 3. It's different down here for 4 sine theta. The center is not at the pole. Since we have a point at 0 and a point at 4 right here, that means our center is actually, so we've got a circle with center. In rectangular, it would just be 0, 2. And our radius is 2. So it goes out 2 in both directions. So that is interesting. It's different. Eventually, you guys are going to be able to look at these equations and tell me that it's a circle and what the radius is without plugging in every single point on here. So again, I probably should have written all of this up here, just so we can get the main takeaways. A circle, the center is no longer at the pole, it's at 0, 2, and the radius is 2, which is half of 4. by the way. Keep that in mind. So turn the page, we have another equation. This time it is 5 cosine theta. So we were doing 4 sine theta. This one's 5 cosine theta. So think about what type of graph this might produce. And we're going to go ahead and plot the points. Just before we even begin, take a look at our theta values. Those are degree values. So what that means is, like I said in class, you guys are going to have to get pretty comfortable switching back and forth between radians and degrees and knowing when to do that. So if I'm inputting a bunch of degree values, I need to be in degree mode. So I'm going back to mode, arrow over to highlight degree, and then we can repeat the process that we just did. Just like the last one, I like to just crunch all the numbers first and then plot points. I'm not really concerned if you fill out this third column here, r comma theta, because it'll just kind of come naturally when you're plotting these points one at a time. So this time it's 5 cosine theta. So 5 cosine 0, we all know that the cosine of 0 is 1. So we've got the r value of 5. Again, I'm not going to plot this yet. I'm just going to crunch all the numbers. Another thing, again, I'm doing second entry so that I can just quickly and easily type in each angle value. So we've got 4.3. Again, tenths is okay, rounding to the nearest tenths. Oops. Second entry, 45. Oops. We've got 3.5. Changing that to 60, 2.5. Okay, I'm gonna pause my recording. I want you guys to pause your video, fill these out, fill this out, plot the points, and we'll see how you do on your own. So again, just make sure you're typing things in carefully, plotting points carefully. When you're done graphing this on your own, hit play again, and we will continue on. If I can figure out how to pause this. Okay. Okay, so I went ahead and finished all of these. I'm hoping you guys did too. Then I started plotting and I decided to start the recording again because I wanted to talk through graphing the rest of these. So these first 5 are straightforward. 5 out 5 at 0 degrees, out 4.3 at 30, 3.5 at 45, and then about 2.5 at 60 degrees. 90 degrees has an R value of 0. So we've got a point right here on the pole. You just can't see it. And then -2.5 at 120. So it can, these grids, these polar grids can really mess with you visually. 120 right here. So with an R value of -2, I'm going to be going backwards. So this highlighter is just kind of to help me keep track of which one of these lines I'm going backward on. So -2.5. So 1, 2.5. So then I pick up down here as my 6th point. Then at 135 right here, which would mean going, so here's 135, so backwards on 135 would be right there, -3.5. 1, 2, 3.5. 180 or 150 right here, going backwards on 150, -4.3, 1, 2, 3, 4, about right here. And then at 180, facing 180, going backwards 5, I would land right back here on my first point. But to ensure that we are totally done plotting points, do one more and just confirm that you would land on the very next point. So at 210 right here, going backwards, that would be right here, backwards 4.3, and we would land on that same one. All right, so we've got all of our points, and connecting these, we see what should be another graph of a circle. So like I said on that last example, eventually you guys will be able to tell from these equations, not only that it's a circle, but what the center is and what the radius is. So we have found that this is a circle. The radius is what? So we look at our radius, the center, if I've got a point at 0 and a point at 5 right here along the polar axis, then the center would have to be right in the middle of 0 and 5. So the center would have to be at 2.5 comma 0. The radius then is exactly 2.5. So r equals 2.5. How do we know that from the equation? Keeping in mind that on the last one that we did, let me put that back for a second. When we did 4 sine theta, we had a radius of 2. How does that relate to the equation? It's half of 4. On this one, we have the 5 out front, radius is 2.5. So what we're gonna start seeing is that this coefficient of cosine and sine is the diameter of the circle, which means the radius is just half of whatever number is out front. The other thing I want you guys to notice is how these are positioned with the horizontal and vertical axes. So this graph of 4 sine theta has this vertical symmetry along what would be the y-axis in rectangular coordinates. 5 cosine theta has horizontal symmetry with what would be the x-axis. So last class, you guys remember me saying we will always be able to associate cosines with x's and sines with y's, or cosines with horizontal symmetry and sines with vertical symmetry. So we're going to see that in all of our graphs of polar equations. Okay, one more graph. I will tell you this one's pretty funky. So turn the page, look at this. I'll probably pause my video in a minute so that I can get all of my R values. I want you guys, again, just practice getting your R values. Let's just stop and look at this equation though first. So this one's very different. We have, instead of just a number sine theta or a number cosine theta, like the 2 graphs we just did, there is a 1 out front. So I'd like to ask you to just think about the effect that you think that might have on a graph. You might be thinking maybe it's a circle that's just been shifted up 1. We'll see. That's typically the guess that I get from students before we graph this. So let's go ahead and fill out the table. Again, in this case, before you even begin, make sure you are in degrees. We were in degrees for the last one, so we don't have to make any changes. And then as we start filling out the values, we're just going to do 1 plus 3 sine 0. Get my value. Sine of 0 is 0. Add 1. We've got 1. Again, I'm going to do that second entry down here. And then all I have to do is go back and type in 30, 2.5, and keep going. So I'm going to pause. You guys don't need me to tell you every single value. I want you guys to go ahead and crunch the numbers, get all the values, practice just quickly plugging and chugging polar coordinates. All right, so I have filled out the rest of my R values here. I do want to start, before we even plot these points, you'll find that instead of seeing these values start to repeat in any familiar way, unlike the other 2, they actually get a little bit weirder after 180 degrees. So this is going to be an interesting graph. So this one, I definitely want to make sure you guys are following along with where to plot these, because it gets a little tricky with this bottom half of values. Again, we've got 1 plus 3 sine theta, so we'll see what type of polar graph we get here. So 0, 1, 0 degrees, and our value of 1. So I've got a point right here. 30 degrees, 2.5. Be careful, because we have degree markers every 15 degrees. So just be careful about choosing only these that we've got on our table for plotting points. 30 degrees, 2.5, so 1, 2.5. 45 degrees, 3.1, 1, 2, 3.1. 60 degrees, 3.6, 1, 2, 3.6-ish right here. So right now it kind of looks like it might be a circle. We've got a circular edge here. 90 degrees, we're out 4. 1, 2, 3, 4. Okay. 120, 3.6. 1, 2, 3.6-ish. 135, 3.1, 1, 2, 3.1. Looks like a circle so far. 150, 2.5, 1, 2.5, 180, 1. Okay, so at this point, if the very next thing I plotted landed right back here where we started, we would then know that we were done. However, it's not. So at 210, our R value is negative 0.5. I'm going to use this highlighter again because it is hard to keep track of what lines are what. So 210 right here going backwards 210. And then our Y value is negative 1/2. So it's actually just going to be right here, which seems a little confusing because now we are on the inside of this figure at negative 1/2. Just keep going. So at 225, which is right here in the middle of the third quadrant, we've got negative 1.1, which means 225 basically is the opposite of 45 degrees. So we're going to be going negative 1.1. So we've got another point right here. Then we've got 240 right here, which is basically the opposite direction of 60. So when we go backwards 1.6 at 240, we're really going in the direction of 60, 1.6. So 1, 1.5, so 1.6 would be about right here. Then we've got 270, comma, I'm down here now, 270, negative 2. Well, 270 straight down. So negative 2 will be straight up in the 90-degree direction out 2. Then we see these values repeating. So at 300, we're at negative 1.6. 300 right here is the opposite direction of 120. So that's going to be out in this direction right here. And then we're at negative 1.6 right here. 315, that's the opposite of 135. So we're going back 1.1. And then 330, I'm down here at 330 at negative 0.5. 330 negative 1/2 is going to be right here. And then 360 out 1. So finally we start that repeat. So this is different from our first two graphs because we were able to stop after 180 on our first two graphs. On this one, we did not get the complete graph or all of our points until we went all the way to 360. So the way that you will connect these points will just be the order that we graphed them in. So starting here on the point 0, or R equals 1, theta equals 0, we're gonna connect this going up along the outside of this figure where it just seems like a circle at first. And then once we get down here to these values that went negative inside, we've got this inner loop of this figure. Kind of almost, I don't know, reminds me of a shell for some reason, or a bead. Okay. So we've got this funky graph of a circular thing with this inner loop. This is a brand new graph you guys have never seen. It has a special name. This is called a limacon. So Limacon. This is a limacon. It is just a polar graph. So we've never seen this in rectangular X's and Y's. Basically, it's kind of like a circle that has an inner loop. Not all limacons have an inner loop. We'll start analyzing these equations more next week. But for fun, we just got to graph our first one. So I'm going to stop here. This will allow you to finish your 8.2/8.3 homework. Before we finish, I just want to point out this was 1 plus sine theta. Remember that we will always be able to associate x's with cosine or horizontal symmetry and y's with sine or vertical symmetry. So this graph of 1 plus 3 sine theta, again, has this vertical symmetry with our vertical axis. Okay, I will stop there. See you soon.